Okay, let's look at one more topic here, shear and moment. So what we're going to do is go inside of a beam and analyze it as best we can. So let's have a look here. What we do with basic statics in equilibrium is we find all the forces acting on an object. We start with the applied forces, and then once we make those assumptions, we do statics and we come up with the reactions. And then once we know all the applied forces and the reactions, that what they do, they cause stresses inside the beam or whatever structural member it is you're designing. Okay, so really what you want to do is to go inside the beam and find the internal forces that it has to resist, which are basically shear and then also bending moment. So shear causes a sliding type failure, as you're seeing there for that top sketch. So if you have shear, you have one plane sliding across the other. So that's shear. The positive convention is as shown there. So the left-hand side would move up and the right-hand side would move down. The negative convention is the opposite. And then the other thing you look at is bending moment, which positive moment bends the beam up. And of course, the way to remember that is positive moment smiles and negative moment frowns. Okay, so that's how we remember the sign convention on that. All right, so what you would do then is it's kind of like the method of sections, where we're going to go inside of a beam and solve for the forces or moments that are inside the beam. So the first job on this is to find the reactions on the beam using statics. And then you cut a section through wherever it is you're interested, and then you do an equilibrium equation on one side of wherever you cut or the other. Okay, so you set forces equal to 0 and moments equal to 0, and then you can solve. Okay, and down on the bottom of the page here, I've got a couple little examples. Page 750. Okay. So if we want to find the shear and moment just to the right of point B, the first thing that we would do there is we would find the reactions on the beam. So I would start, with a moment about a pin joint. If you look at the reactions here, there would be reactions at A. That's a pin right there. So that has an upward reaction and a sideways reaction. And then we'd have a reaction at the roller. I'd take a moment about A. 30 times 1.5, that'd be negative, and 90 times 1.5 and 1.5, that's 3. So 90 times 3 would be negative. And then we've got 5 times the reaction at D. So the reaction at D is 63. Then the sum of forces, we got RAY up, 30 and 90 down, and then 63 up, so RAY would be 57. Okay. So we'd want to start with the reactions. Then what we would do is we'd cut at whatever location we were interested in and find the internal force and the internal moment. So if I were to cut just to the right of B, okay, or just to the right of the 30 kilonewton load, I guess I should say, at B, what I'm going to solve for now, if I make that cut, is I'm going to put internal forces at that cut, where I've cut the beam open. So I've got a shear force that is positive downward, if you look at that sign convention at the top of the page. And then I've got a moment there that curls the beam up and is also positive because it curls the beam up. And what I would then do is find the internal shear and the internal moment. Okay, so the shear is, I solve for that. So I do sum of Fy equals 0. I got 57 up, 30 down. Now I'm on the static sign convention now, so I'd have a minus V sub B. and I could solve for V sub B, it would be 27 kilonewtons. So what's happening inside that beam at point B is it has to develop 27 kilonewtons of shear force to stay together. If it can't develop that, if it can't generate that, it'll break. That's what it'll do, okay? So really, to design a beam, you want to know what those internal forces are, because that's what the beam has to resist, so to speak. Okay. Similarly, I could do a moment. Usually I do it about the cut. So I'm going to have 57 kilonewtons times 1.5 meters. That's negative because it's clockwise. And then I'm just to the right of that 30 kilonewton load, so that's pretty much a zero distance, so I don't need to worry about the 30 kilonewtons. I don't need to worry about the shear at B because I'm right there at B. So those both essentially have zero moment arms. And then I've got a counterclockwise M sub B. So M sub B is 85.5 kilonewton meters when I solve for it. So that's the internal shear and internal moment that I can find. Okay, right there. And that's what's going on inside the beam at point B. So, got any questions on that? Are we doing okay with that basic idea there? Okay. So those are the values you pull out when you start to design the beam. Those values there. Yeah, why don't you work on the right there? I've got that internal shear and moment on there. Why don't you just find what the shear is at C and the moment at C? Okay. This is some FY and some moments about that cut. I'm doing okay. So 63 for the shear. And then 94.5 for the moment. So looking all right. Doing okay. Okay, so we got 57 up and 30 and 90 down. And now the shear is kind of funny. The positive convention for shear is down, so you draw it down as you work from left to right. The convention on these things is to work from left to right. And then when you put it into the statics equation, the sum of Fy, it goes in as a negative because it points down. So we're kind of on the static sign convention when we do that. And then we could solve for it. And in this case, we get a negative answer, which means it actually acts up, which is a little convoluted, I guess. But the shear is always a little funny. I just draw it down and I forget about it. Just solve for it. And then the moment there, we've got the 57 has a 3.5 meter moment arm, negative because it's clockwise, 30 with a 2 meter moment arm positive, and 90 with a 0.5 meter moment arm positive, and then the unknown MC, solve for MC, and it's 94.5. Okay. So we're good with that? Okay. All right, so what we're doing there is just solving for those internal forces. You do have to find the reactions first. You have to do that. The convention is to work left to right.
So why did we have to find the shear in order to perform that moment again? I know it's like if it's supposed to work.
Actually, you don't. If you take moments about the cut, you don't need to know the shear to do the moment. But you do want to solve for both because you design a beam for both shear and moment. So they're both things you want to know. All right, so let's look at now, that's step one, is to solve for shear and moment. Step two is to find equations, because what we just did, we found shear and moment at a particular point. The next thing to do is to write up generalized equations, okay? So, and that will give you the shear and moment anywhere in a beam you want to know. So if I have this situation here, 6,000 newtons pushing down on that beam, you know, what I would do, I would find the reactions first. So I'll take moments about A, 6,000 by 1.6, that's negative. And then the reaction at C times 2.4 is positive, so 6,000 and 1.6. And then the reaction at C pushing back up with a moment arm of 2.4. So that'll get you the reaction at C, and that's 4,000, and then some of Fy will get you the reaction at A, which is 2,000. Okay. So again, always find reactions before you jump into this. All right. Now, what's going to happen here as you're going through this process is you're going to need two sets of equations. Every time you have to draw a new free body diagram, you need a new equation. So the beam anywhere between A and B will have the same free body diagram. As long as you haven't yet got to that 6,000 Newton force, the free body diagram will look like that, okay? But once you get to the 6,000 Newton force, the free body diagram changes into that. And it'll stay in that form until you almost hit point C, just a little bit short of it. So anytime you need a new free body diagram, you have to draw that up and generate a new set of equations. That's the rule on this stuff. You start from left to right and work your way through. Okay. So what I would do, I would cut anywhere between A and B and draw up a free body diagram of what I got there to the left. And then I'd put the unknown shear and moment on my cut and solve for them. So sum of Fy is 0. That'll get me 2,000 up minus VAB. So VAB is 2,000. That's the shear anywhere between A and B. And then I can sum moments about the cut, and I'm going to have the unknown moment inside the beam of MAB. And then I'll have 2,000 times X coming around clockwise, so that's negative. 2,000 is the load, and X is the moment arm. So the moment anywhere between A and B is 2,000 times whatever that distance X is. So I set X equals 0 on the left, measure any distance between A and B, plug that in and multiply it by 2,000, I'll get the moment. That's basically the deal, okay? So now instead of just having the moment at a point, we've got it anywhere from A to B. Okay. All right with that. All right, let's have a look here from B to C. All right, now once you get past B, you pick up that 6,000 Newton load. So we'll start at A, measure to the right, we'll call that X. That's the convention, okay? So now we're just looking anywhere between B and C. That distance from A to B is 1.6. Okay. So that'll go in as a number, and then I've got a variable from A to wherever I'm making my cut. All right, so I can add a couple little things to this. Let's put the shear and moment on there. On that end where I made the cut, that's where the shear and moment go. And really the things to remember about this is the shear goes down and the moment is counterclockwise positive. It curls the beam up. Okay, so there's the shear and moment. Now I'm going to need distances there to get moment arms. I've got that distance to the 2,000, but what's that little distance going to be from the cut to B? This little distance right here. What is that?
X minus 1.6.
There you go, yeah. So whatever value X is, if you take 1.6 away from it, you'll get that distance, see? So that's going to be that moment arm I'm going to use to the 6,000. So I'm going to want to put that in there, see? Because that'll be a moment arm I'm going to use. And see, that'll hold for any distance X as long as we're going between B and C. So anything between 1.6 and 2.4, that'll work, okay? So we'll put that in there, and then off you go. You can go ahead and solve for the shear and the moment, okay? And it's just a matter of working through the shear and moment with a sum of Fy is 0 and a sum of moments about the cut is 0, and then you can solve for those, okay? So that's that's what we're up to with this. Now we use this in strengths a lot because what we do in strengths is we take what we're doing here in statics and then we find the internal forces. And then we use those internal forces and some design equations to design the beam. Okay, so I'm getting VBC there is negative 4,000, and that holds anywhere between B and C because I just have discrete loads on there, and the sum of them works out to be that 4,000 difference there, I guess the difference between them, you would say. Now, I get an equation for the moment because the moment arms are constantly changing as I work my way across from B to C. So I'm going to get sum of moments about the cut is 0 is negative 2000x plus 6000 times its moment arm, which is x minus 1.6, and then plus MBC. Okay, so I'll take that MBC, which is what I'm solving for, to the other side of the equation, and then I multiply through by -1 because I want to solve for positive MBC. When I take the MBC over, it becomes negative, so I just multiply everything through by -1 to get the positive MBC that I want to solve for, and then I collect terms. So I'm going to have MBC is 2000x minus 6000x minus 1.6, and then that's 2000x minus 6000x plus 9600, so that's negative 4000x plus 9600. So you can plug any value of x you want in there between 1.6 and 2.4, I think it is, and that'll tell you what the moment is. Okay? So it varies.
The negative shear is pointing upwards?
Yeah. Yeah, as you work your way from left to right, negative shear actually points up, yeah. A little funny, but that's just how the sign convention works. And again, on that, just draw the shear down when you do your free body diagram, and then forget about it. Don't
Always draw it down?
Yeah, just draw it down, and you don't have to think about anything else. Just solve for it in a statics equation. Don't worry about it after that. Okay. All right. Now this is, if I were doing a structural software program, I'd program my software to do this, to come up with these equations, and I'd plot up the equations. So I'd have an equation, and with that I could find the shear and moment anywhere. But also you can make plots of them. So it's very common to come up with shear and moment diagrams, they're called. And there's actually rules to draw those up kind of from scratch without having to generate the equations. If you know a few rules, you can draw up a shear diagram and a moment diagram. So I think if I were doing a simpler problem, if I were a structural engineer, I'd just draw up the shear and moment diagram. That's really about all there is to it. This is the common way to do things if you're doing it yourself, is to do a diagram, because the equations can get kind of complicated and long and a little onerous. So it's quicker just to draw these diagrams. So what I've got here is a table that has the value of shear and moment in the different locations. So from A to B, it's shear is 2000, M is 2000x, M is moment there. And then from B to C, shear is negative 4000, and the moment is negative 4000x plus 9600. So given that information, I can draw up a shear diagram. It's just 2000 from A to B, and then negative 4000 from B to C. So it's just two blocks, basically. And then I can also draw up a moment diagram. So it's a straight line from A to B with an equation at 2000x. So that slopes up with a slope of 2000. Its y-intercept is 0, so it starts at 0 and just slopes up till then. Then when I get to B, the equation changes to another linear equation with a negative slope, negative 4000x plus 9600. Okay, like so. So that's a shear and moment diagram. Now those are kind of handy because you can just look at them and get a feel for what the beam's doing. You can't really do that with an equation, but with a diagram you can. Okay. Often the governing factor on designing a beam is moment. Okay. Shear comes in sometimes, but on the longer beams especially, it's moment. So notice when you look at that diagram, notice what happens at the ends. The moment kind of tails off to 0. When they built North Santiam Hall, we went in there and had a look at it. The joists for the floors are actually trusses. They look like that. Okay, whatever, however they put them together. But, I was noticing that the supports, they got quite thin at the supports there. And then, you know, I was talking to the engineer about it, and the engineer was saying, well, you know, we ran our shear and moment diagrams, and the moments are quite low at the supports at either end, so we didn't bother beefing them up. Okay? Save a little money there. Okay. You ever seen a flatbed truck going down the highway? They look kind of like that, where they got the wheel wells cut out. Now, when you design that, you could design it like a beam, right? It's a beam supporting a load. Now, it's in a truck rolling down the road, but it's a beam with a load. That's how I would think about that if I were designing one of those. Same sort of thing here. See, when you start loading this thing up with whatever you're carrying on it, the moment magnitude is going to be quite low at the ends, which is where the wheels are at. So you could probably get away with carving that beam back at the wheels because there's not that much of a moment, which is quite convenient because you can fit the wheels in there, see? So that's why, you know, this visual information can be very helpful when you're looking at it. Okay. All right. So, we can do the Cliff Notes version of this. So let's just look real quick at how to draw these diagrams. We'll get into this quite a bit more in strengths. Let's at least look at it. The rules are on page 790. So what you do when you draw diagrams is you go from load to shear, shear to moment. You walk it down. I even line the diagrams up on my page so I can do that. So for shear, the value of the distributed load at a point equals the slope of the shear diagram at that point. So if the distributed load has a value, that equals the slope of the shear diagram. Now what we're doing as we walk our way down is a graphical integration process. So the change in shear between 2 points is equal to the area under the loading diagram between the 2 points. Okay, those are the two main rules. And then if you have a concentrated load at a point, you get a vertical line on the shear diagram of equal value at that point. So a concentrated load makes the shear diagram change immediately. Now for moment, the value of shear at a point is equal to the slope of the moment diagram at that point. And the change in moment between 2 points is equal to the area under the shear diagram between the 2 points. So what we're seeing here, the rules for going from load to shear are the same rules that are used to go from shear to moment. Namely, the value of that diagram is equal to the slope of the diagram below it. And the change, the area under the diagram is equal to the change in the diagram below it. Those are basically the rules right there that we'll use, okay? So, why don't we apply those rules to what we were just looking at here. Okay, so we'll go back a little ways and we'll just look at this. So I'm back on page 770. So I've got a loading diagram up above this thing. And, you know, notice I've got the shear and the moment lined up. If I were doing this, you know, like I set them up for your homework, I've just got a piece of graph paper and everything just lined right up. So what I've got there is I've got a loading diagram. Like so. And I've got what, 2,000, 6,000, and 4,000, right? So I got 6,000 right there, and I got 2,000 right here, and then I got 4,000 right there. Okay. So if I go down to that shear diagram, I start at 0. These diagrams always start at 0. I'm gonna jump up from 0 to 2,000 immediately. So what I'm doing, I've got my starting point at 0, and I go up by the load, which is 2,000, so that equals 2,000. Okay. Now from there to the 6,000 load, I've got nothing going on. There is no change, there's no distributed load. So the slope here equals the value of the distributed load, and the distributed load equals 0. So there's no change. And in a common sense perspective, there's nothing going on that beam that will change the shear. It just stays flat. Okay. It hits this point here at B. Then you've got a 6,000 load that goes down. So we're at 2,000. We drop by 6,000. And of course, that equals negative 4,000. So that's how you end up at negative 4,000. Once again, there's nothing on the beam there that'll change this shear until you get to the reaction. And the reaction takes you from negative 4,000 back up to 0. Okay. So there's the shear diagram. And once you get comfortable with it, you know, that takes you 30 seconds to do, you know, once you get comfortable with this process. No equations, no messing around with that stuff, just draw it up. It's quite a bit simpler, okay. Okay, now to make the next step here, what we do is we look at the area under the shear diagram, because the area under the shear diagram is the change in the moment diagram. Okay, so you just find these areas. So that first area is 2,000 times what? How far over is it? 1.6?
Yep.
So that first area equals 3,200. And the next area is a negative 4,000. Sorry if this is getting a little messy in here. Times 0.8, thank you, 0.8. And that's negative 32,000. Or 3,200, I should say. So what that does to the moment diagram is you start at 0. And then from there you go up by the area of the shear diagram. And you go from 0 up 3,200, so you get up to 3,200. The slope of this line equals the value of the shear, and that's 2,000. Once you're at 3,200, then you go down by this second area right here, down by 3,200. And that gets you to 0. And the slope of this next line is the value of the shear, and that's negative 4,000. Okay? Gets you back down to 0. Now, like I say, we're a bit short of time. We'll get into this more in strength of materials for those of you that take it. But, you know, you could draw those things up. Once you're comfortable with it, just bang, bang. It's pretty straight up. Okay? So I'm going to get you just a couple of these to do. They're the same problem twice, once with a diagram and once with an equation. These aren't, you know, I've got the solutions posted in Moodle even, I think, if you want to look at them, it's fine. So 381 and 391. They're the same problem, you just do it once with a diagram and once with equations. So 381, 391. And I think, yeah, due next week, along with those two moment of inertia problems, okay? All right, now those of you that have that physics class, probably what we'll do is just have you take it, if you can, earlier on Tuesday. Just talk to me individually, we'll get something scheduled out. If that's a huge problem, let me know. You know, we'll figure something out that works. Okay. All right.
Is the Shear and Moment going to be on the final?
I don't know. I'll figure that out tomorrow. But I'll let you know for sure tomorrow.